Alright, let's talk about this very important gas called oxygen. It is very important to us because without oxygen, you cannot actually survive. But apart from using it for respiration, we actually use oxygen for a number of applications. So that therefore means that understanding the properties of oxygen, physical and chemical properties, and its usage becomes very, very important. Okay, so we are going to look at this gas that we know that by proportion, in terms of volume proportion, it's about 21%. And if you remember that the most abundant gas by proportion is actually nitrogen with 78%. So the next gas there that follows nitrogen is oxygen. Oxygen exists on its own as oxygen molecules, but can also be found in other compounds such as water, mineral oils, and then proteins, glucose, so even carbohydrates, vitamins, lipids. You'll find oxygen there. Okay, so we have oxygen that we breathe in, but is also incorporated into other important products, okay, or compounds. So, like I said, all plants and all animals, humans inclusive, use oxygen for respiration. And the type of respiration where oxygen is needed is what you call aerobic respiration. Okay, so that means that without oxygen, we cannot burn nutrients to get energy. Okay, if you're sick and your respiratory system is not taking in enough oxygen, or perhaps you're actually anemic, and that means that the red blood cells are not carrying the sufficient oxygen that you need for your body, then that means that you'll be given what you call oxygen. And that's what we are calling medical oxygen therapy. Okay, that means that manufacturing oxygen and giving it to patients is very important in the hospital, in management of different diseases. And then you have seen people who are doing welding. They make doors, they make sometimes even chairs using these metals that they weld. So oxygen is an important gas in welding and also in cutting metals. And then you have oxygen also being used very much in aerospace and also in mining, and also in the laboratory. For example, oxygen is also used in a number of chemical reactions. Okay, in the aerospace, actually oxygen is used as a fuel. So rocket propulsion, and that is basically liquid oxygen. That means that a capital oxygen can be turned into a liquid form, that is liquidified oxygen. Oxygen is also used in the treatment of water, that is to say that making water pure and good for consumption. Okay, ozone production for disinfection, that is also another use of oxygen in chemical synthesis in different industries, and also even in marine or submarine systems underwater. Okay, life support underwater requires individuals to have oxygen. Even people who go to the space craft, they need oxygen to be able to go to areas where we have limited oxygen. Okay, so oxygen is very, very important in a number of uses. So oxygen is a colorless gas. It is tasteless, and also it is odorless. It is slightly soluble in water and slightly denser than air, and boils at negative 183 degrees centigrade, and then also freezes at negative 280 degrees centigrade. Okay, these are basically the physical properties. Now we can talk about the chemical properties of oxygen, and we are starting with the reaction of oxygen with what we call alkali metals. These basically include sodium and potassium. These are the ones we are going to use, but of course we have lithium in there. Okay, so these metals basically react with oxygen to form peroxides and also oxides, depending on how much oxygen is actually available. So if we have excess oxygen, that means that we have a lot of oxygen, we form peroxides. So sodium reacts with oxygen to form sodium peroxide. Okay, that is when you have excess oxygen. If you have limited oxygen, this is to say you don't have a lot of oxygen, you form that is sodium oxide here. That's what you will form. Okay, but when you dissolve the products, whether it is the sodium oxide or the sodium peroxide, you get sodium hydroxide. For example, for the peroxide, when you react the sodium peroxide with water, you get sodium hydroxide plus hydrogen peroxide. And then if you react the sodium oxide with water, you get sodium hydroxide. Okay, the same reaction in terms of the products is what you get when you have potassium. When you have potassium reacting with water, the reaction will follow the same pattern as the reaction with sodium. So potassium forms sodium and potassium peroxide, and also forms potassium oxide, depending on how much oxygen you have. If you have a lot of oxygen, then you're going to have potassium peroxide. If you have less oxygen, you're going to form potassium oxide. And also this reacts the same way with water. If you have potassium peroxide, okay, potassium peroxide, you react it with water, you'll form potassium oxide plus hydrogen peroxide. But if you have potassium oxide, reacting it with water, you will form potassium hydroxide. Okay, that is with the alkali metals. So we move to the other metals. Group 2 metals, the reactions are that you have a metal oxide being formed. So for example, magnesium burns in oxygen to produce magnesium oxide, which is white. Okay, so this is the equation there. And then if you add water to the magnesium oxide, you get magnesium hydroxide here. Okay, that's what you will get. And then calcium, they react basically the same way. You form calcium oxide. That oxide, if you add water to it, you form calcium hydroxide. Let's look at the reaction with other metals. Okay, with the iron, basically when iron reacts with oxygen, you form what we call rust. When you leave iron nails outside, they will get rusted. So that rust is actually iron 3 oxide. Okay, iron 3 oxide. This iron 3 oxide is insoluble in water and will not have any impact on the litmus paper. That means that it will not indicate whether it is acidic or it is neutral. When it comes to copper copper burns in oxygen to form copper 2 oxide. The reason as to why we have this 2 oxide even lead here, these are basically elements that have varying valences. Okay, varying valences. So still copper reacts with oxygen to form copper oxide. The same thing happens when you have lead reacting with oxygen. So if you heat lead in oxygen, you get lead oxide. If you heat copper in oxygen, you get copper oxide. Okay. With nonmetals, starting with the reaction of carbon with oxygen, you will form carbon dioxide if you have a lot of oxygen. But if you have limited oxygen, then you're going to form carbon monoxide. And let me include that equation here. So you're saying carbon plus oxygen, that is in limited supply, you get a gas that we call carbon monoxide, and that is how it is written. We need to balance this equation. So this is carbon monoxide here. So this carbon monoxide is actually poisonous because it competes with oxygen to be captured by the red blood cells. So the red blood cells will go for the carbon monoxide, leaving you without oxygen, and this will cause suffocation and death. Okay, and I've explained this several times that this can lead to what you call carbon monoxide poisoning, which can happen in our homes when we have stoves that we leave inside our rooms while we are sleeping, and the doors and the windows, and there are no ventilators. When everything is closed, that means that the carbon monoxide will accumulate and then suffocate you to death. Okay, so that is something that you can note there. When you add water to carbon dioxide, you form a weak acid that we call carbonic acid. So this is carbonic acid. It is actually a weak acid, and we shall see what a weak acid is. It does not completely disassociate, okay, to form hydrogen ions. Other nonmetals that we can look at are phosphorus. Still, the extent to which you get the products depend on how much oxygen you actually have. If you have limited oxygen, that is to say that you don't have a lot of oxygen and still the reaction is happening at low temperatures, you will get what we call, this is capital P, you will get phosphorus 3 oxide, okay, phosphorus 3 oxide with 4 phosphorus atoms there, okay, at low temperatures and limited oxygen supply. If you have high temperatures and a higher or excess oxygen, then you're going to get phosphorus 5 oxide, okay? You're going to get phosphorus 5 oxide, okay? So what happens? The reaction of oxygen with phosphorus depends on the conditions that we have. At high oxygen concentration and high temperatures, you will get phosphorus 5. At low temperatures and limited oxygen supply, you get phosphorus 3 oxide. Okay, that's what you get. Now, the reactions of these compounds with water gives you different types of acids. So with the reaction of phosphorus 3 oxide with water will give you what we call phosphorus acid, and then the reaction of phosphorus 5 oxide with water gives you what we call phosphoric acid. Okay, so you can see these things that we talked about in naming compounds and naming acids. These are suffix that we added, OUS, and then RIC. Okay, RIC. Sulfuric acid, nitric acid, and then now we can see phosphoric acid. Okay, so the equations are basically here. That is for formation of phosphorus 3 oxide, the formation of phosphorus 5 oxide, and then the formation of phosphorus acid and the formation of phosphoric acid. The difference between this and that is related to how many oxygen atoms are we having. Here we're having 4, here we're having 4, here we're having 4, here we're having 3. Okay, that's something that you can note there. And then another non-metal that we can look at is sulfur. Also the reaction here depends on how much oxygen you actually have. If you have limited oxygen, you form sulfur dioxide. This is sulfur dioxide, the gas that you form there, and it's basically burns with a blue flame. Sulfur burns with a blue flame, something that you need to note here. Okay, and then you have this gas, that sulfur dioxide is actually colorless, but it has a pungent smell, a pungent odor. In presence of more oxygen, you form what you call sulfur trioxide. So this oxygen becomes a 3 in that reaction. This is sulfur trioxide being formed here. Okay, so this is also where we are having sulfurous acid. You can still see the suffix there. You can also see the suffix here. And the difference is basically here you have 4, here you have 3. Okay, there. So how do we prepare oxygen in the lab? Mainly in the lab we decompose potassium chloride. Decomposition means breaking up, and we usually use heat. Thermal decomposition of potassium chloride is the major way of producing oxygen in the lab, but we can still use decomposition of hydrogen peroxide in the lab. Potassium permanganate is not commonly used, and then also mercury oxide is not also used because of the toxic fumes that can be produced, so you don't want to use that. Okay, so basically this is to say that oxygen can be produced by, let us say, 2 main ways, but that is not to say that there are no other ways of producing it, but perhaps those ways are not basically ideal for use. So usually we focus a lot on potassium chloride and also hydrogen peroxide. So what do you basically need? For you to see what we need, see the setup. The setup is just here. This is what you need to set up. You need a source of heat. This is a Bunsen burner, okay, to heat the potassium chloride. But this reaction happens in the presence of a catalyst here, manganese 4 oxide. You need it. So when you're heating a mixture of potassium chloride and manganese 4 oxide, which is acting as a catalyst. Okay. This test tube is held in a stable position, just like what you see using a Todd stand. And then you have a cork here to hold this tube properly in place. This is what we call a delivery tube. Okay, a delivery tube, and then you have this water trough, and then you have this water jug here. It is inverted on water. It is inverted in water here. This is what we call a beehive. Beehive shape. So the gas jar is inverted onto the beehive shape. So when you heat here, the oxygen will be emitted and to be collected over water there. Okay, so that's the process of preparing oxygen in the lab. Okay, so the reaction is here. Potassium chlorate is heated to give you potassium chloride, and then the oxygen will be involved. You need to balance the equation. So this is 3 to make 6. This is also the oxygen is also 3 to make 6. Potassium 2, and then the chloride 2, also 2 this side. Okay, I really hope that you're very familiar with balancing this equation. It shouldn't be very difficult. Okay, so still I maintain that manganese 4 oxide is used as the catalyst, and then also the gas is collected over water, because we say it is just slightly soluble in water, right? So that means that you can collect it over water. If it is completely soluble in water, you can't collect it over water. Okay, and then this is downward displacement of air. This method of collecting this gas here is what we call downward displacement of air. Okay, so laboratory safety measures, always take note of them. What you need to put on your PPE, and then handle potassium chlorate carefully. It may irritate you if it gets into contact with your skin. So always when you're heating, be very careful. Don't inhale any gas that you produce in the laboratory. You can also produce it from decomposition of hydrogen peroxide. The setup is a little bit different. Still, you will have potassium dioxide here as the catalyst. You have the hydrogen peroxide up there. You release this, and then the gas will be evolved and still collected over water. So basically the procedure is not different. Okay, manganese 4 oxide still as the catalyst. Okay, so this is the equation, the decomposition of the hydrogen peroxide to form water and oxygen, which you are interested in, still collected over water, okay, through downward displacement of air. How do we know that the gas we are dealing with is actually oxygen? We have 2 tests that we can perform. The first one is what we call the glowing wooden splint test. So you get this, it's just glowing, it's not that burning. But when you put it in a container, this is the conical flask that contains oxygen, you see that it will rekindle it. It will now start burning. That means that the gas that is inside there is oxygen, because oxygen is the gas that supports burning. So when you lower a wooden splint into a jar containing oxygen, it will reignite it and burn. Okay, vigorously. So that is one test. Another test is if you have a candle that has been burning for some time and has a flame. When you lower it into still a container with oxygen, the burning will be more vigorous. It will intensify and be giving you brighter light. That is to say that the gas that is there actually supports burning, and that's why the burning increases intensity and burns more brightly. So that is also another test for oxygen. Okay, so thank you very much for listening to this presentation where we have looked at oxygen. We recognize that oxygen is used by organisms, but also we apply it in a number of explorations, in welding, in diving, in using it as in rocket propulsion, and many other things. Oxygen is very reactive. It reacts with the alkali metals, it reacts with alkaline earth metals, and also reacts with transition metals such as copper, lead, and iron. Okay, usually they have oxides that are being formed. When the reactions, for example, with the nonmetals, for example, sulfur, carbon, these reactions depend on the extent to which we have oxygen. If we have limited oxygen, the products are different from when we have excess oxygen. Okay, but however, with these nonmetals, when the products that are being formed, which are usually oxides, when we react them with water, we form acids. Okay, we can form sulfurous acid, we can form sulfuric acid, depending on what are you reacting with what. Okay, and we have seen that to produce oxygen in the laboratory, you basically need potassium chlorate that you thermodecompose. That means that you heat it, and usually this happens in presence of manganese oxide, which acts as a catalyst. You collect the oxygen over water. Okay, you collect the oxygen over water. Thank you for listening.